So, good afternoon. I am Francesco Lanza. I am a PhD student at the University of Palermo. Today I will talk about learning plans with NARS. Before starting my presentation, let me introduce myself and my research interest and my research field. Since I started my PhD, I was fascinated by human-robot interaction and the robot too, clearly. Specifically, I was fascinated by cooperation and collaboration of human and robot at every level. In this talk, I will discuss a method based on NARS for letting robot and agent create plans at runtime. Clearly, for increasing and enhancing the quality of human-robot interaction, and specifically in the teaming domain, we should endow robots or in general intelligent agents with the ability to plan at runtime. This led us to define novel skills and to reproduce human skills such as self-adaptation and imagination. Clearly, these skills are not simple to realize, but if we want to move a step toward this direction, we should think how to reproduce it, and clearly a step toward is letting agents to plan and learning plan at runtime. But we will see what means and what I intend for learning plan at runtime. Following our previous work, clearly, on multi-agent architecture for human-robot teaming interaction, we will discuss a system able to learn plan using NARS. This system merged the qualities and the characteristics of BDI agents with the logic underpinning the non-axiomatic reasoning system. And we will see why. In this slide, it's reproduced an outline, very simple outline of the talk of today. In the first part of the talk, I will describe the instrument and the logic that conducted me and the collaboration with Patrick and the Temple University in general to produce this kind of work. In the second part, there is the description of the work. So how to compose, how to write plans, and how to let the agent writing these plans, and so learning plans with NARS. I say that when I started my PhD, I was fascinated by human-robot teaming interaction specifically. And clearly, before to start to develop a system, human-robot interaction system, software system that let robot interact with human in the proper way, I started studying actually the human-robot interaction system that clearly was developed during this time. And I try to find which points are mandatory to build a human-robot interaction system. After studying these systems, I focused on the implementation part. So I focused on which instrument, which tools is good for implementing a human-robot interaction system. I'm not focusing on now human-robot interaction impact on humans, but I'm focused more on how to build a proper human-robot interaction system that is able to cooperate and collaborate with others. So I extract some points that, in some sense, are relevant for my software architecture, and I thought about that. If I work with someone, clearly. So if I am in a team, the team member has to know the overall goal of the team, clearly to work together, the team move toward to reach a specific goal. A team member on a knowledge base that contains facts and concepts about the world. What this means? This means that me and the rest of the team has to share knowledge. We should talk with the same language, and we should give the same meaning to the same concept to understand what we should do. A team member is also aware of the surrounding environment. I should know, or at least I should be able to understand what are in the surrounding environment. A team member is to be able to communicate with other teammates. Clearly, for letting communication, collaboration, cooperation between human and robot, they should speak the same language. They should interact and using vocal or other kind of languages that are common for the human and for the robot. The team member has also to be able to delegate or to adopt actions or tasks by other teammates. It's clear because let's try to imagine that I am a robot and my teammate that is a human delegate me some tasks. The human has to know which limitation, which constraints I have, ethical constraints, but also physical constraints. In the same sense, I am a robot, and if I have to delegate a task or an action to a human, I should know how it is, its physical limitation, ethical limitation too, and everything that clearly it's relevant for reaching the target, for executing the task. A team member so has to be autonomous in decision making, to be proactive and satisfy the overall goal. This means that the team member has to be exactly proactive in the sense that it should take decision without asking everything if it's right or it's not. It should be so aware of itself, and so it should show self-consciousness abilities, but also theory of mind abilities, because it should be aware about abilities, limitation, and behavior of the teammates. So this is important for building a software architecture that, in some sense, is able to realize a human-robot interaction software architecture. In general, this is a standard scenario in a human-robot interaction. When certainly a robot that has to collaborate with a human use its abilities to cooperate and collaborate for reaching goal. We can see the cloud. When inside the cloud there is a kind of simulation of the world. This is how to realize a kind of imagination. We want to endow the robot with this facility, this ability to imagine what happens in the world. And in some sense, this should let the robot also to try to find to understand how the world will evolve during the time. But I talked about multi-agent architecture, software architecture, and so on. But how I can realize a software architecture that is able to implement a natural software system. And that led me to define all of the points that I showed before in the slide. Studying and analyzing the agent-oriented software engineering, I see that the multi-agent paradigm is clearly and certainly one of the most proper methodology, and it suits with everything that I defined. But what is a multi-agent system, and so the multi-agent paradigm what involved? A multi-agent system is a form of machine-to-machine communication. It enables different type of AI system to communicate with others. We can consider it as a direct consequence of the agent-based system. And according with the definition that we give for a multi-agent system, it enables agents to interact and exchanging relevant information for producing behavior that are not only processed by a single evaluation. What I mean? I mean that if an agent-based system, so an agent could communicate with other agents and let communication between AI system, and an ABS system is also implements communication with agents implementing a set of rules and constraints. It implements a kind of communication that is not directly. So, agent-based system that is able to communicate with other agents, but it shares results, not methods, and how to reach the results. This simple change into the paradigm basically change completely the framework, and this change completely how the agent work. This is a simple agent that clearly sense the environment, produce some action, and this will act on the environment, performing operation and modifying it. Clearly, this is a loop, and each time the agent percept, reason, and act on the environment. Which is different with a multi-agent system. A multi-agent system is different because we have the environment that it presents a problem to multi-agent system, and the system interface of our multi-agent system will distribute this problem to all agents deployed into the multi-agent architecture, and all learning AI systems that are into the multi-agent application are able to communicate with others, basically, and try to find altogether a solution that best fit the problem. So we can compare an agent-based model with a multi-agent system, and we could say that a multi-agent system is an evolution of the agent-based model, and it implements everything that is that could provide a better solution respect an agent-based system. It is decentralized, lets interconnectivity, are autonomous, robust, reliable, efficient. So we use this paradigm to implement our software architecture. But there are several types of framework that implements multi-agent system, which I can use to develop. Basically, we moved our attention to the JSON framework. JSON is a multi-agent framework based on Jade platform. Jade is another framework that let developers create multi-agent application. Specifically, JSON, the difference with Jade basically is that we can define agents that employ the BDI paradigm. Clearly, the BDI best fit with our concept of human-robot interaction, because each agent inside the multi-agent framework follow this kind of model, and so all agents inside the multi-agent system move toward this model, and they exploit goal, desire, intention for reaching clearly try to reach the solution and try to accomplish the overall goal. So JSON use the AgentSpeak as a formalist, so as a language for implementing and the logic that underpins the agent reasoning system. JSON is written in Java and use classes for rendering plans, agent architecture, belief base, message, whatever. But what are inside an agent in JSON? This is the reasoning cycle that is developed is deployed into an agent, an JSON agent, and it starts, as we can see from our perception, to produce an action applying clearly the reasoning process that here is figured. We can see that we have beliefs defined after the block, the perception block. These beliefs are handled and events are generated, and after that, a process, an unifying process, will select a plan that best fit with current perception for produce an action or a message through an intention that is clearly executed. Which is the model, how the model is built. This is an UML diagram of the agent framework. The JSON framework is open source framework, and we can customize it, and we can use it, and we can extend it as we want. Basically, in this UML diagram are figured all classes relevant for implementing and for extending the JSON framework as we want. The agent implements clearly all functionalities, all methods that are relevant for the agent, like so just select message, select event, select option, that if you look inside the reasoning cycle are the action that led, are the function that led to choice that which intention should be selected to be executed, and at the end that act into the environment. And we have also the age arc class, the agent arc class, that contains methods for acting and perceive the environment. We have also other classes, such as the belief base or the plan library, that we can customize and we can build and we can extend as we want. So Now we will talk about the how to learn plan with NARS. The main ingredients that we need to know to work with to produce this kind of method are beliefs, plans, and reasoning system. So basically, beliefs are information that the agent has about the world. Decide are all the possible states of affairs that the agent might like to accomplish. Intention are the states of affairs that the agent has decided to work toward. Okay, perfect. Generally, belief in programming language based on logic are represented as a collection of literals. But if we want, we can also defining a different type of structure that contain the belief base, and we can use as belief base, database, a text, a simple file, simple text file, or everything. Decides, what are desired? Having a decider does not imply that an agent acts upon it. So potentially, a design may be not a completion never during the agent life, but it's a potential influencer of the agent's action. Sometimes some desires could not be never reached during the lifetime, as I said, and also could collide with others. Intention may be goals that are delegated to the agent or may result from considering option. So what are intention basically are the way how to act to reach the goal. Okay, so what is a plan? And now NARS could create a plan using AgentSpeak, because we said that to program agent, we need to know AgentSpeak language, and clearly an agent programmer has to define a plan library that represents the reasoning system that underpins the programming, the logic of the programming that I'm writing for letting agent operating into the multi-agent architecture. So I mean, the plan uses the first order logic. It is composed by of two parts: the head of the plan and the tail of the plan. The head is characterized by two other parts: the triggering event and the context, and the body that contains other subplans, internal actions, communication actions, belief-based revision actions. What are these? We start from the triggering event. The triggering event tells the agent which are the specific events that trigger that plan. So I mean, when an agent see a specific event is rated up, so it knows that this is the plan that is to be launched, that is to be executed. So once the event is triggered, the plan is executed if preconditions are satisfied. This precondition, we will see that are into the context. So when a plan is triggered by an event, this means that the plan is relevant with the event. So high confidence. Pay attention to this term, high confidence, because this term is at the base to create plan with NARS. This concept is at the base because NARS will exploit this kind of high confidence for producing plan, but also for retracting plan. Context. What is the context? The context is the last element that match with the head of plan. It represents all precondition that has to be exist for executing the plan. Clearly, dynamic environment and changing contexts are complicated to deal with. Clearly, for facing this problem, an agent programmer generally write alternative plans. But you know that it's impossible to predict all possible plans. And sometimes the agent programmer has to write some recovery plan that, for example, put the robot in a safe mode. Clearly, what means this during an interaction with a human? This means that the robot has to stop its execution, and so the interaction is not so an interaction, no? Because the robot stopped to work, and the human that is cooperating with the robot see a robot that is stopped. So this is not good, because a human expects that the robot try to find a solution for accomplishing the task, for reaching the goal. Okay, so for learning new plans, NARS will use the alternative plans to manipulate them and trying to find a possible solution. NARS so will take in consideration these plans, so all plans that the agent programmer put into the plan library, and it will try to transform and manipulate them for letting agent learn a new one. Clearly, the context of a plan is used for checking the current situation to apply the plan. And this means that NARS has to take also in account these preconditions. Preconditions are important to create a proper plan and that they could be applied into the domain. The body. What is the body of a plan? The body of a plan is the easiest part of the plan to understand because it represents the set of action, the set of other plans, sub-plans, activities, messages, whatever the agent has to perform for reaching the goal. It is a generic, it is known also with the word formula, and each formula in the body does not produce necessarily an effectors. Should be, for example, a check of some engine into the robots. The body is the ultimate relevant part of the plan. And this is what this is the difference. When I wrote several plans, clearly, generally they change for precondition, but also for the body, because with the body I write the receipt, a kind of a receipt that I will respect, that the robot has to perform for reaching a solution. So NARS, when it has to write a new plan, has to think about the triggering event, but also precondition and the set of actions or formula that has to put all together for realizing a new plan. And this kind of formula, the body, should be has to respect the precondition that NARS has selected, because NARS cannot write a plan that where the body doesn't respect the precondition. So it's a very complex system, and such a very complex system we should understand, and we should try to find a solution that fits with everything basically. So now I show the NARS-based method for composing plan during agent execution. So this is the AgentSpeak control cycle. We see the reasoning cycle of a generic JSON agent. And we see the JSON control cycle. So if we change the point of view and we focus on the goal addition relation, so it means that we focus on reaching a goal, the JSON agent works in this way. It tries to find in its plan library an applicable plan. If a plan is found, it continues its execution, pushing the plan into the intention queue, processes the intention, and if everything goes well, it's fine. The agent achieved the goal, otherwise it failed. But what's up if the agent does not find a proper plan? Clearly it failed directly. So the agent is stopped basically. And this is not good, we said. So we have to modify this JSON control cycle, because we want that that the agent try to find a solution and try to continue its life cycle, producing some action that clearly are relevant for the domain. How we can do that? We can do that exploiting the characteristic of the JSON framework that are called recovery plan. So JSON let agent programmer to define recovery plan, but it's always the agent programmer that has to write the logic of this recovery plan. It's not the agent itself that try to find the solution. Generally, in a recovery plan, we can find something that could handle the error. It's a kind of exception handler, if you want to see in this way. But clearly, it's not sufficient for a nature I domain. So we exploiting another characteristic of the JSON framework that are the internal actions. We, through internal action and through recovery plan, extend the standard JSON control cycle, including another important characteristic for the JSON agent. That is the internal action for to invoke NARS. What means that Learning JSON is not able to implement a method for revising its knowledge base and its plan library without clearly intelligent support. It's not able JSON to find an alternative plan through composition processes of its plan library and clearly or exploiting its knowledge. For implementing this, we need an external support. We put inside the JSON agent the external support, and this external support is NARS. NARS provided the needed support. So this is the NARS module appeared from looking from an external point of view. This is how it works. The NARS module is deployed into the architecture, and it is called invoking an internal action for the agent. So from a programming point of view, the JSON agent programmer has not to know nothing about the NARS and Narcisse. Has only to, when he found inside the code a critical section, he could write a recovery plan where the body of this recovery plan is only invoke NARS. So it's like to say, I don't know how to handle this situation. I will try to give this control to NARS, and if NARS is able to find a solution, it will give back and will push the plan into the plan library of the agent, and the agent will produce other actions that clearly aren't defined at the same time. So NARS take into account goal, beliefs, and plan library, convert the term, the AgentSpeak term in Narcisse term, invoke the NARS planner. If it will face clearly no plan not found and the agent is informed, otherwise it reconvert the Narcisse term into an AgentSpeak, create a plan, and push into the plan library the new plan. So the agent now has produced autonomously and without any external support, human support, a new plan. So you learn something that no one has told it before. This means extending the control cycle in this way. So if we have to accomplish a goal and we don't find a proper plan that fits with this goal, we will launch NARS reasoning system, and after that, if a plan is generated, we push into the plan library that will be pushed into intention. Once we process this intention, what's up? It will process it, and we will inform NARS about the success or the failure. What means that? It means that NARS, informed by the successful of the plan or failure of the plan, could change its truth value, or better, the truth value assigned to the new plan. And once these clearly fall below a threshold, the plan is retracted from the plan library. So what this means? This means that if NARS is able to add a plan into the plan library, and this plan seems to be a valid solution that could be applied into the domain for pushing the objective and reaching so the goal. In the case of this plan is not good and it will continue to fail, the truth value of this plan below a predefined threshold that we measured experimentally during our execution, but we are working to make these threshold dynamic. If this plan, if this threshold fall below, it will retract because NARS will inform the agent that, sorry agent, but the plan that I generated for you, it's not valid because it fails, and so it's not valid. It's better to retract this plan. What it means that NARS is also able to delete from the current plan library all plans that are not relevant for the scenario that is facing. So we can manipulate, we can perform operations that are compliant with the domain and with the context, without losing time, without waste time with the plans that are not relevant for the scope of the mission of the team and so on. So the agent learns what is good and what not for the current context through its direct experience. And in this sense, the agent learn new plan at runtime. For future work, we are integrating this system with an advanced simulator for letting agent and robot test their plans before executing them. We realized that the simulator based on a real engine for letting robot imagining its action, so to reproduce the action inside its mind and see before it performs the action to the real world if this action is valid or not. This, in some sense, should endow the robot with an imagination skill. We are conducting other study, and we are realizing other models. Also, Patrick said before, we are realizing a NARS Module for letting the usage of NARS in with every robot, basically supported by the robotic operating system, clearly, and we are also investigating the possibility to realize a complete multi-agent framework that works completely with NARS, because NARS has all characteristics that support HRI in the large sense. So I think that that's all. Thank you for your attention, and I hope that you enjoyed this talk.